Welcome to the Mathematics of Thinking. In this playlist, we'll be diving into famous variety of algorithms. We'll be breaking them down into visuals and in order to understand how they empower every tool we use every single day as a data engineer. So yeah, let's get started. So today's video will be talking about the topological sort. And by the end of this video, you will understand how Apache Airflow knows which task to run before which every single time your DAG fires. So imagine yourself trapped in this situation. So you just joined the data team. Every morning at 6 a.m. you have 15 tasks that need to run. Some tasks can't start until other finish. So you can't run the transformations before the ingestion is done, and you can't run the aggregations before the transformation. You can't send the business reports before the aggregation, and you have 15 of these with hundreds of dependencies between them. So get the order wrong even once and the pipeline crashes, so the data is wrong, reports are late, and the business is angry. So how do you figure out the correct order automatically every single run without a human manually sorting it out each time? So the answer is topological sorts. And once you understand it, you will see it everywhere, and Airflow is using it, Spark uses it, and your compiler uses it, npm uses it, every familiar or a famous algorithm, tools using it. So now let's understand what is a DAG, because it's an important concept that we have to learn about, which is the DAG. So before we look to the algorithm, we need to understand what it operates on. It's a structure that's called a DAG. It's a directed cyclic graph. We have three words, so let's break them each on its way. We have, first of all, graph. It's just a set of nodes connected by edges. In our case, nodes are the tasks and edges are the dependencies between them. For directed, it stands for the direction of the edges, because edges have direction. If there is an edge from A to B, it means that B depends on A, not the other way around. And we have acyclic, that means there is no circular loops. And this is very, very important, because a task A cannot eventually depend on itself, so directed or indirectly. And if it did, you would have a deadlock and a chicken and egg problem that we all know, with no solution. So look at the bottom of this slide. That is an example of a DAG. So here we have ingest, and then flows into a validate. Then we have clean all the way through to report, no cycles, clear direction, a valid execution order exists. And now the algorithm, the one that solves this, is, there are two classic approaches to the topological sort, which is the def-es based, and Con algorithm, which is a if-s based. I will show you Con. It's more intuitive and it gives you cycle detection for free. So we have 4 steps, that's all. We have the step 1, which counts in degree. For every node in the graph, count how many other nodes points to it. That number is called the in degree, and in degree of 0 means that a node has no prerequisites. It is ready to run immediately. The step 2, seed the queue, find all nodes with in degree 0 and add them to the processing queue. These are your starting points, your roots. So the third step is to process and unlock pop a node from the queue and add it to your results. Then for each of its neighbors, reduce their in degree by 1, because this node is now done. So one of their dependencies is resolved. If any neighbor now has an in degree 0 added to the queue, and it is now unblocked. So the fourth step, the cycle detection. When the queue is empty, you have to check if your result contains all the nodes. If yes, you have a valid topological order. If no, some nodes were never unlocked, which means a cycle exists and the source is impossible. Now we have the in-degree. So let me make the in-degree concept concrete before we look at the code. So the in-degree is just how many tasks must complete before this one can start. In degree 0, it means that no prerequisites, run it immediately. In degree 1, one task must finish first. In degree 2, two tasks must finish first, etc. Look at the right panel. We have our full data. Our full data pipeline with in degree only ingest raw data has in degree 0. That is the only starting point. Aggregate revenue has in degree 2, and if it waits for both transform sales and transform users, and when we process ingest raw data, we decrement validate schema from like 1 to 0. So it joins the queue and the chain continues like that. Now, let me trace through the algorithm on our actual pipeline. So we have the init. So we count all in degrees, only ingest raw data is 0, queue is seeded. The step 1, we pop the ingest raw data, add it to the result, we visit its neighbors, and validate the schema and decrement it from 1 to 0. Validate schema joins the queue. Now the step 2, we pop validate schema, same thing, clean data drops to 0 and joins the queue. Step 3, this is the interesting one, which in here we pop clean data. It has two neighbors, transform sales and transform users. Both drop to 0, both joins the queue simultaneously. This means they can run in parallel, both have no remaining dependencies. This is exactly how Airflow dispatches them to separate workers. So, step done, we process with transform, aggregate revenue and locks, then we load to warehouse, then send reports. All 8 tasks are in the results. Valid order found. So here is the clean Python implementation. Let me walk through it. So we start with the importation of the default DECT and DQ, which are the two standards, library tools. Default DECT to safety track in degree without key errors, and DQ for efficient complexity of O to 1 for the pop left from the queue. And now let's build the function, starting by building the in-degree map so that we can iterate over every edge. Every time we see an edge pointing to a node, we increment and will be incremented by, let's increment its in degree. And after that, we will be seeding the queue with every node that has the in degree 0. And these are our starting points. They have no dependencies, and then we'll be creating the loop for the BFS. So to pop a node and add it to the results. Then for each of its neighbors, the decrement their in degree, if any hit 0, then push them into the queue. So that's what we're going to be doing here.
So let me just try to fix this to make it more readable. They will be using the pop left from the cube. This node and maybe the list in here. Then we'll call the in degree. I always miss between the blankets and the brackets. I think maybe this method will be taking time, like the talking about coding in this session. I guess for the next episodes I will be just maybe explaining the code, write it before the recording. I mean, that could save us some time. So now finally we'll be implement the cycle detection if the result length does not match the total number of nodes, the length of in degrees. Some were never reached. That means a cycle existed. So we'll be commenting in here. It means that we have a cycle, so we return none. This is exactly the check that makes Khan's algorithm safe to use in production.
Now the direct connection to Apache Airflow. When you write a DAG in Airflow, those Python files with DAG and task decorators, Airflow parses that file and builds an internal graph object. Then it runs this exact algorithm, Khan's topological sort, to determine the correct task execution before scheduling a single job. So look at the right panel in here. That is your DAG, okay? It's broken into execution levels. Level 1 runs first. Level 4 has two tasks, transform sales and transform users, which run in parallel on separate workers. And if you accidentally create a cycle in your DAG, Airflow throws an Airflow DAG cycle exception at part time. That is a Khan cycle detection firing before a single task is even scheduled. Now let's talk about some complexity and limits. I mean, there are a few things that you to know before using this in production. The time complexity, it's O of V plus E. V stands for vertices, and it's the number of nodes, and E stands for edges, which is the number of dependencies. You visit every node once, you process every edge once. Linear, extremely fast. For the space complexity, it's OV, so just in the degree map and the queue. So the three limits to remember are: first, this only works on DAGs. The moment you have a cycle, the topological sort is undefined. It's like you divide on 0. Always include cycle detection. So the algorithm we talked about, which is Khan, give it to you for free, okay? The second thing to remember is the output is not unique. If two tasks have no dependencies between them, either can came first. Airflow handles this by running them in parallel when possible. Third, the third thing that you have to remember, which is use the level-based variant to identify which tasks can run in parallel. I showed a version of that in the Python file linked in the description. It groups tasks by execution level and is what Airflow builds its worker scheduling on. So yeah, I mean now let me wrap up with 4 things you know now. The topological sort orders nodes in a DAG so that every dependency always comes before the node that depends on it. 2. Kant's algorithm achieves this in OV plus A time using in-degree counting and BFS. Cycle detection is built in. 3. Apache Airflow uses this exact algorithm to determine task execution order every time your DAG runs. 4. The level-based variant surfaces which tasks can run in parallel. That is Airflow worker pool logic in a nutshell. So if this was useful, hit like, drop a comment with the tool you have used that you know, realize, run the topological sort under the hood. Next episode we'll be talking about Dijkstra algorithm, how Google Maps finds the shortest path through a million node graph in milliseconds. The hook is going to hit different. So see you there. By the way, if you are new to Python, I'm launching a Python formation. You can subscribe by filling the form in the description.